I'm going to talk today about architecting next generation AV autonomy stacks. And in particular, as we've seen today here at the symposium and kind of in general through the AV field, there's really a big push now in moving away from kind of the traditional, let's say, pipelined classical autonomous vehicle architecture of perception, prediction, planning, and control into next generation stacks. And in particular, there's been a lot of emphasis on how we can bring in machine learning and deep learning into these stacks, which have really driven a lot of new research into novel end-to-end architectures, but also novel infrastructure around those architectures, for example, in simulation, in order to make training and evaluating these models easier. So today in particular, I'm going to talk about two of our research works along both of these directions. So the first is going to be in a systematic characterization of end-to-end architectures and analyzing maybe which choices matter and which ones matter less so. And then I'll also talk about dynamic scene reconstruction, which is along our efforts to really make creating simulations and really high fidelity sensor simulations much more practical and easy. So without further ado, let's dive into the first topic. So as we've seen in this year, and actually, for maybe 3 or 4 years up till now, there's been quite a growing amount of work in end-to-end autonomous vehicle stacks. And, each of them have kind of unique, distinct designs. At least this year alone, there have been 3 or actually 5 papers which have really made quite a high impact. One of them was even CVPR's best paper, which was UniAD. However, even with all of these recent works, and all of the strong performance that they've shown, it's not very clear which architecture is the best, so to speak. For instance, there's been a lot of representations that have been proposed in each of these works. And, I think it's not really clear. Is one better than the other? Should we combine multiple? How should we actually choose these? And even beyond just information representations, what kinds of modules do we actually need in our stacks? How should we place them? How should we connect these inputs and outputs of these different modules together? And so in one of our latest works, which will soon, fingers crossed, hopefully be on archive, we've actually dived into really systematically exploring some of these choices and understanding which ones matter for overall stack performance. And we've analyzed these along 3 key dimensions. So the first is necessity, understanding which tasks or modules are actually essential for the downstream task of driving, and if there are maybe any redundancies, and maybe we can remove some components that might just be wasting computation. The second is placement. So how should we, once we've chosen our set of modules, how should we arrange them in a stack? Should they all be, one after the other, sequential? Should they be all in parallel, executing at the same time, or maybe some hybrid? And then finally, there's a question of representation. So when you're passing information between modules, should we use latent features, like, for example, transformer queries, or should we use a little bit more interpretable outputs like bounding boxes, or maybe semantic bird's eye view features, or a combination of both? And here, what I've done is visualized these papers from this year on end-to-end driving in kind of a common representation format. So, we can see that even though each of these papers have really achieved strong performance, they actually do so in quite different ways, with different choices of modules, different choices of information, passing between each stack. And it's, just kind of briefly visualizing what they look like here. So before we can actually dive into systematically exploring this, we first need to come up with a, common unified evaluation platform, because otherwise we'll, have no idea what we're doing. And unfortunately, actually, up until now, there's really been no standard benchmark in each of these prior works. They're all going to make a few slightly different changes, which maybe it makes sense for their work, but it's going to make comparing across works quite difficult. So we use a suite of metrics, and we're primarily evaluating using the new scenes data set, which is something that has been very common in prior works. And typically, they also evaluate an open loop, which means you're just kind of making your prediction of what the ego vehicle should do, and then redoing that at every new time step. And particularly, we're interested in evaluating collision rate, accuracy in terms of what the actual human did in the data set, and how well the motion complies with the map. Does it stay in lane? Does it stay on the road? And we've chosen to standardize along the following choices. So when we're computing collision rates, we include vehicles and pedestrians, not just one or the other. We also include evaluations with agents that have partial futures. So even if you're towards the end of a scenario, it's still worthwhile to evaluate that. And finally, we also ensure that each model has at least 2 frames worth of input, because sometimes if you're evaluating, for example, acceleration or velocity, you actually need to compute that from multiple frames. So we just want to make sure every model has at least these bare minimum choices. So when we take all of these into account and we compare some of these recent state-of-the-art models, I think there's quite a clear story that you can see coming out, and it kind of matches what we even see if you just look at the papers themselves, which is that basically, kind of following sequentially the release of these papers, you see, okay, UniAD, or what's it called? VAD performs better than UniAD, and then ADMLP performs better than VAD. And, these models are each kind of following their architectures that I showed in those colored boxes. But what's one thing that we see is that while the collision rates and L2 errors, kind of compared to human driving, maybe there's a consistent story there. It seems like a little bit we maybe give up some of the map understanding in achieving that. And some of that is because, maybe sometimes reviewers focus on performance on some metrics versus others. But one thing that I want to point out is that in the full validation set, a lot of the driving is quite boring. You have really a lot of straight line trajectories where you don't really need to have a very fancy model and actually to do anything. And there's not too much interaction with other agents. So we also took a look at some targeted evaluation where, when I say targeted, it's really nothing that fancy. We just ignored completely straight driving scenes. So here, these are basically all scenes that have a turn to the left or the right somewhere in them. And what we find is actually quite interesting. The collision rate, which otherwise looked quite, very nice and very low in the above plot, actually grows quite a bit between these different works. And the L2 error now has a much, the story is really not that clear in terms of which one is better when you compare on these kinds of more interesting scenarios. And so, we wanted to, in setting up this work, we kind of saw these comparisons and we're like, okay, let's try and get down to the core of what matters and see if we can maybe, more systematically explore some of the choices made here. So in order to do this, we started first from the UniAD architecture, which is visualized here. And we said, okay, what if the first thing that we do is we remove these edge number 1 and edge number 2, which are kind of grayed out here. And what those edges are is basically the direct use of mapping features in motion prediction, as well as the direct use of the occupancy, the predicted occupancy in motion planning. And what was very interesting was actually removing these edges improves performance quite significantly, actually. And it's, it's a little bit strange, but when we dived in to understand why, it's because the lane queries, in particular, those transformer queries that were being passed between modules were actually quite noisy. And further, the way that information was being passed from occupancy to planning was there was like a test time optimization step. And while this makes sense online, the problem is it wasn't factored in during training. And so you kind of have this unmodeled disturbance or influence, which actually was yielding some very jagged trajectories when you actually deployed it. And they're not really human-like. So, okay, interesting. So starting from this baseline, what about some of these other edges? Interestingly enough, they kind of don't matter too much. We remove, again, the paper has quite long tables which detail each of these, the effects of doing this. But really across the board, there's not much, too much of a change in each of the metrics that we were evaluating. And, we found that actually, even if you try and add back those edges that you remove, and maybe you choose some different representations, that actually decreases performance. And so we said, okay, this is interesting, but, it looks like for a lot of these, intermodule dependencies, actually the main thing of importance is maybe the features towards the beginning rather than, how these modules are influencing each other. Okay, interesting. Let's keep that in mind. Something else we wanted to understand was, the presence of maybe any redundance in some of these modules. So one maybe obvious one that's visible is we have kind of 2 prediction modules here in this architecture. We have one that predicts trajectories, so it's kind of a very sparse output, and one that predicts occupancies, which is basically, taking your trying to estimate like a probability heat map over time in the future. So it's much more dense. And what was interesting was actually the performance of having these modules is effectively the same if you take one out but leave the other in and make sure to pass that information to planning, or vice versa. So, we saw that this extra redundancy basically means that you can achieve the same performance with or without one of them. But what's interesting is on the very left, if you don't have any connection to planning and you just have these modules effectively as auxiliary tasks, if you remove one of them, either of them, actually it significantly decreases performance. So what's interesting is when you have these in a parallel design, they're actually both extremely important to learn a good representation. But when you have them sequentially influencing planning, you actually have redundancy and you can kind of remove one of them. Moving on to the second component, a big part of autonomous driving is simulation. And a big part of simulation is creating really realistic, high-fidelity worlds in which you can train or evaluate your, let's say, chosen autonomous vehicle stack. And creating some of these worlds can be quite difficult, right? Especially if you need to have someone who brings in, for example, a lot of assets or 3D textures and all this information to actually construct the world. It can be quite expensive and labor-intensive. And so a very big question nowadays is, if we have a real-world driving log that contains posed RGB images and LiDAR measurements, is it possible to accurately reconstruct and represent the scene, and most crucially, including dynamic objects? And one of the big questions that we had in the group was, especially last year and the year before, there's been a lot of hubbub about the performance and strength of neural radiance fields, especially for modeling, 3D environments, static 3D environments. And I have here a very nice video from, I believe this was Waymo from, from last year. And, you can see it's a really fantastic reconstruction of the world, albeit it's kind of a reconstruction of the static world. So the big question here is, can we leverage this high fidelity NeRF-based reconstruction of the world and simultaneously model dynamic objects without requiring ground truth annotations or maybe auxiliary models to kind of help remove those dynamic objects from the world? So, typically if you're asking a question in a talk, the answer is going to be almost certainly yes, absolutely. And we do this with one of our latest works called EmRNeRF. EmRNeRF is, at its core, a method that decomposes the dynamic world into three core components. They are a 3D static neural field, which contains all the stationary elements in the world, a 4D dynamic field. I say 4D here because, we want to query not just XYZ, but also a time step in which this object is moving, containing all the mobile elements in the world. And then we also have a 4D flow field, which really helps to build correspondences between the dynamic elements across time steps. And most importantly, this decomposition, which I'll show what the results look like, this decomposition is learned entirely from self-supervision. There are 0 labels that go into any of the training of this model. And there's no even auxiliary models to give, for example, optical flow or something like that, which I know can be quite common. All we do here is reconstruct the original sensor data. So let's take a look at what this kind of a model and world representation gives you. So I think probably one of the most obvious things, and I mean, NeRFs, can do this, so it's not really that surprising, but you can replay, right? You can reconstruct the world and you can resimulate your sensor data. So, I mean, even for those of you sitting here, it's going to be very difficult to see some of the artifacts, if any, between these two. But I mean, yeah, trust me, they are kind of two separate videos. And not just, can we do this in 2D, but of course, since we have a 3D or 4D representation of the world, we can also do this in 3D. And in particular, this can be very useful if, for example, you collected maybe let's say you collected LiDAR measurements with like a 32 beam LiDAR, but you actually want to try, what if I have 64 beams or 128 beams? You can, by having this world representation, you can densify, you can kind of simulate if you had a denser LiDAR. And we can do this with very high fidelity. So here we're also measuring the difference between ground truth and resimulated LiDAR using the chamfer distance, which is a common measurement of the distance between two point clouds. Now, where it gets really interesting is, like I said, we decompose the world into these three components. So you can actually visualize and independently render these. And I think this is one of the biggest strengths, actually, of EmmerNerf. Again, 0 labels, absolutely no ground truth labeling. And we're able to get this kind of a decomposition just from training. So you can see how, all the static objects are captured here in the middle, and all the dynamic objects are very nicely segmented out. One thing I want to point out that's kind of interesting is that even, it's not necessarily objects that could move, it's objects that did move. And so you see some kind of stationary pedestrians here that are static through through the entire scene. And so they're kind of left to be part of the world. Now, we can also, like I said, this is 2 of those components, right? The static field and the dynamic field. We also get a scene flow understanding from this decomposition. And so for each of these dynamic objects, we can also visualize how they, change frame by frame. And of course, all of this, I'm showing here in 2D, but of course we have this actually in full 3D and in particular full 4D, where basically what we can do, so this is just a visualization of kind of the entire scene at one point, but we can also move, a slider here to kind of visualize every time step and understand. Here we're specifically plotting the actual flow on the, on the corresponding points in the real world. So you can kind of see how the model actually understands the motion of these objects. And then finally, a very classic NERF capability is novel view synthesis, where basically you can, have your motion through the world, but you can kind of move your camera now independently around it. Now, while this is very common in NERF that you can kind of explore spatially the world with your camera, in this method, you can actually explore temporally the world as well. So here, what we do on the very right image, so after we do this kind of freezing time and moving the camera, you can freeze the camera and move time. So if you take a look on the right video, you can kind of see how once we freeze the camera, you can see kind of the rest of the world kind of just keeps trudging along, right? Because now the ego vehicle that was collecting data is also moving along with all those other vehicles. So you can do these kind of very interesting things with time as well, because you have a 4D representation. So this is all great. We're very happy. But so far, we've only been reconstructing sensor data. And there's, of course, other kinds of information that we might be able to use. So one of the core questions we had when we were looking at this work was, what if we also tasked EmmerNerf with reconstructing some semantic features? And there's been some very powerful recent examples that have been released, like models like DynoV2, which are visual foundation models that have a very strong understanding of semantic components of images. So we said, okay, all this is just another feature that we can add to our sensor data that we can reconstruct, and let's try it. Let's see what it looks like. So we tried this, and then we kind of saw these very strange patterns in the resulting rendered images. And we were like, okay, that's very strange. You don't typically see these in the papers of these kinds of works. And what we actually found was that these patterns are actually caused by the positional embeddings used in transformer-based models like DynoV2. And they actually yield artifacts when you kind of reproject them back into an image. And so, okay, that's kind of annoying. I'm not going to talk in too much detail, but in the paper, we actually found a way to basically decompose even these kinds of artifacts. Because if you think about it, all they are camera motion independent artifacts. And just like we segmented the world into 3D and 4D, we can also segment these artifacts away from the resulting image. And you can see here on that second last row what the clean image looks like, how actually these features are now much nicer and stable, and they're actually nice and even semantically meaningful. And I'm going to show a specific example of what this looks like here in 4D. So when we do lift these DynoV2 features from their original 2D to the 4D world, you can see some very interesting things here, like how all, for example, cars are typical. So here I'm clustering the features into, I just did PCA in order to basically get RGB colors for each of the, the features that these objects are, that these objects have. And what you can see is that basically all vehicles here are this kind of same shade of light blue. Buildings, it looks like, they have some purple hue, and then, the traffic infrastructure like signs and lights are this kind of green color. And what's very, powerful about this is now we can actually think of these kinds of nerfs, not just, I mean, for simulation, sure, but for auto labeling, right? For world understanding, just by collecting, driving logs with 0 labels. And that's not all, right? So, I mean, Dino V2 is one potential choice of model, but there's many other of these kinds of vision foundation models. For example, Clip from OpenAI, which actually allows, it was kind of built to be tied also to text. And so some things you can do is when you project these up to 4D, you can query for certain things, right? You can say, okay, if I query for a car, which are the features in 4D that align most closely with these? And you can actually see how, in a completely unsupervised fashion, we're able to really identify cars or other kinds of things in scenes. And it's kind of interesting, if you query for traffic sign versus traffic light, you get kind of 2 different umbrella categorizations of, all kinds of signs, like, even road markings, versus just the specific, hanging infrastructure over intersections. And we can even take this kind of idea and maybe use it for example, auto labeling of dynamic objects or tracking them throughout the world. And so, here we have, all of those vehicles that we can, identify as being similar. We can cluster them in, it could be PCA space, could be whichever other feature space you want, and basically track them over time, because we have each of their motion through the frames. We have the flow information. We have all of this information. I have a demo of this, but I'm going to get through the rest of the slides. And then if you guys are interested, I'll bring it up and we can take a look at what that looks like. So wrapping up a little bit, now I think is really a fantastic time for AV research. I mean, obviously I'm going to say this, I do it, but the reason why is because really, compared to some years ago, there's now thousands of hours of public data sets that are available for researchers to use and build upon. And they're, from really many different locations in the world. It's not just one city or one country even. You have a pretty good covering of the world, actually. The only problem is each of these public AV data sets also have a very unique format. And so unfortunately, if you've worked with some of these data sets, it's actually quite difficult to, let's say you train your model on one, then you have to spend like 2.5 weeks to, change your encoder to work with the other representation. And I know one of the posters actually is also in the room, also addressing this problem. So we've also built something to help tackle this in NVIDIA, which is a unified trajectory format and API for data loading. So in particular, we've developed Traj Data, which is a flexible, open, and extensible interface to multiple human trajectory data sets. And actually, we'll be presenting this here at NeurIPS. It's in the datasets and benchmarks track, just after this talk from the 5 to 7 p.m. Poster session. I'll be at number 126 if you have more questions about this. But what we found in developing this is that, just by making, cross data set work easier, you can even enable almost immediately new lines of research, like, for example, analyzing how methods for prediction generalize from one city to another or from one country to another. We've also seen how it, at least internally, how it simplifies research development and actually accelerates research work. And finally, we've released it under the Apache 2.0 license to really ensure that anyone who is working on this kind of research can, use it, contribute to it, benefit from it, etc. Lastly, I want to, give a little shout out to, of course, the rest of the group, which does, all of this fantastic work and much more. We have 4 main pillars of research that we do in the work, in the research group right now. The first is, of course, end-to-end AV architectures, some of which I talked about today. The second is understanding how we can use foundation models, which could be LLMs or vision foundation models or other kinds of models for AV use cases. We also do, as you can imagine, quite a bit of work on simulation, especially for the verification and validation of autonomous vehicles, but also to use them for example, closed loop training. And then lastly, of course, we have a big thrust on safety, where, especially as the industry and research is moving away from some of the more traditional, formally guaranteed safe autonomy stacks into more AI-based, perhaps more performant, but maybe less guaranteed stacks. We're also moving towards understanding basically new frameworks of safety that we can apply to these stacks to still, ensure safety, even if we can't guarantee it from the ground up. And some examples of work we do in this space include conformal methods, building runtime monitors, understanding out of distribution cases, anomaly detection, et cetera. If you have any interest in any of these, please, take a look at our website or talk to myself or any of the other members of the group who are here at the conference. So lastly, I think the key takeaways that I want to impart here are, the first is that at least for, strong open loop planning performance, all you really need is a parallel AV architecture where you learn a good representation using a lot of auxiliary tasks. And it's, as you can imagine, significantly faster than a sequential or a hybrid design where you have to run things in iteration or, one after the other. The second is that closed loop simulation is really going to play an increasingly important role in AV training and development and evaluation. And especially really the key component to make it useful is a data-driven human and environment modeling. I know today I talked about environment modeling, but we also have a lot of work on agent behavior simulation for traffic simulation. And I think these are really key enabling capabilities to bring simulation into that step where it can be useful beyond purely verification and validation. And finally, working with multiple AV trajectory data sets has really never been easier. So thank you all for your time, and happy to take questions, and please check out any of these links if you're interested in more work.